Okay, so welcome everybody. So today we will have a tutorial on the Yambo code, and I start with this presentation where I give you an overview of the Yambo code and of the main features, and I will speak a bit about the performances of the code, just a few slides. So I'm Davide Sangalli from CNR Monterotondo, and I'm one of the developers of the Yambo code. So this is very briefly the outline of my talk. So first I will present what is the Yambo code, and then I will speak for most of the time about ab initio many-body perturbation theory and the quasi-particle concept. So up to now we have seen code based on density functional theory. Today we somehow switch topic, and although the Yambo code is still based on the density functional theory, but we move to another level, which is many-body perturbation theory. And then in the last part, if I will have time, I will also present how many-body perturbation theory can be used to compute the physical properties of excitons and optical spectra of materials. So let me start with the code. The Yambo code is different from the code you have seen so far, because as I said, it's a code which is mostly based on many-body perturbation theory. And as you will see in the tutorials, one of the key differences is that you do not start from scratch, but you actually start from a density functional theory performed with another code, which can be, for example, Quantum Espresso. And then starting from Quantum Espresso, there is an interface which converts the output of Quantum Espresso into the format of the Yambo code, and then you can perform calculations based on many-body perturbation theory. So as other codes is you have seen in this school, it's a quite sophisticated code. It relies on a number of libraries. This is just, I mean, the name of few libraries is not even updated. But most importantly, the code has an active community of developers. And so here you see the faces of some of the developers. It doesn't include all the developers also because this slide was done a couple of years ago. So I'm sorry if I miss some of the newest developers. And then the idea is that every developer usually start working on the Yambo code because he is interested in a specific project, so maybe in computing some specific physical properties of the system, and then these properties enter in the code and are made available to the community. So which are the properties which can be computed with the Yambo code? Here there is a list, and the first two are the most important, or I would say the core of the code, the quasi-particle band structures and the optical properties and the physics of excitons. But then Yambo can also compute magneto-optical properties, dichroism, can do real-time propagation, linear optics, and different things which you're not going to see in the school. And again, the philosophy is that all these are released GPL, so they are released to the community. There are other properties which are under active development. They are not yet released, but the philosophy is that they will be released once they are ready for the users. So the code is based on plane waves, so it's, let's say, tuned to work, to be efficient on extended systems, 3D materials. But it is also very efficient in computing the properties of 2D materials, one-dimensional materials, and can be even used for isolated systems. So you can find all the information on the website, which you see here in the center. But beyond the website, we also have, let's say, some material available online. There is a wiki with tutorials. There is a forum where you can register and ask questions to the Yambo team. There is a repository hosted on GitHub from which you can download the source. And also we periodically organize schools like this one. Schools like this one, or even other schools which are more focused on the Yambo code by itself, and where you can see more in details what the code can do. And there is a growing community of users. Here is written more than 200 publications, and also this number is a bit outdated. Now it's even larger. And as I said, today you will see the two main features, and in particular, we will focus on the quasi-particle properties. I will give an introduction here, and then Alberto, with the next presentation, will speak more in details about quasi-particles. So I want to guide you a bit through what is ab initio many-body perturbation theory. Now we start from this object, which is called the time-ordered Green function. It is this function which has this expression. It's the expectation value on the many-body wave function of these field operators with a time ordering operator, say, deciding the ordering of these two operators. Now, in a nutshell, the time ordering makes the Green function having two terms. And these two terms, which are here in the blue one on the left and the red one on the right, can be interpreted in a very physical way. So in the first term, you start here from the ground state, you remove an electron, so you create an hole here at position r and time t, and then you measure the probability of finding the hole, so you create back the electron at position r prime and t prime. So it describes somehow the propagation of the hole inside the many-body system. And the other term is basically the same, just with the times operator inverted. So instead of first creating a hole, this time you create an electron. This dagger means electron creation. And again, you create the electron in some place, and then you measure the probability of finding the electron in another position. So why is this useful? Well, what you can do, you start from this expression, and then you can insert in between these two field operator some completeness relation. And in particular, you insert a sum of overexcited states. And since on one side you remove a hole, and on the other side you added an electron, you have a sum of states with m-1 and m+1 particles. And then from this expression, which is called the Lehmann representation of the many-body Green function, you can take the Fourier transform. So these are functions of time. And these operators include the Hamiltonian of the system. Since the Hamiltonian acting on the eigenstates gives the eigenvalues, then you can take the Fourier transform and you obtain this expression. So you see that one important feature of the many-body Green function is that it has a poles structure. So it contains at the denominator these poles, which are the energy differences between the ground state, E naught, with m particle, and excited states with n-1 and n+1 particles. So why is this structure important? Because these poles are exactly what is measured in a photoemission experiment. So this is sketched here. So you have a materials with a valence band occupied by electrons and a conduction band, which is empty. Now, if you want to probe this valence band experimentally, you do photoemission, you remove one electron, and you detect the energy of the electron. And this energy is precisely this energy difference, which can be computed through the many-body Green function. And same for the conduction. Instead of doing photoemission, you have to do what is called inverse photoemission. It's a less common technique, but still it can be used to measure the conduction band, where you add one electron and you measure the energy at which the electron is captured. So this is all nice, but of course we need a way to compute the many-body Green function and the poles of the Green function. So the many-body Green function, as I said, is the expectation value of the many-body system, so the m-particle electronic systems, which is sketched here, where you have a number of electrons which are all interacting among themselves. So imagine that here these electrons obey this Hamiltonian, where they have a bare term or a non-interacting term, which can be, for example, the kinetic energy plus the external potential due to the ions, plus a term which describes the interaction among the electrons, which is depicted here by these arrows. Now, what can be done through many-body perturbation theory, and thanks to this theorem, it's called the Gell-Manello theorem, you can rewrite this green function as the expectation value over a wave function, which is a wave function of non-interacting particles. Now, of course, since you remove the interaction from the ground state, the price to pay is that you have the interaction back inside the expression of the expectation value. So you see here the green function is a sum of many terms and going to 0 plus up to infinity, where the interaction term appears 0, 1, 2, up to n times. So all these interaction terms can be rewritten in a form of a self-energy. So the two key ingredients of many-body perturbation theory are now the non-interacting wave function, which can be computed easily because now we have non-interacting particles, plus all the, let's say, difficult part of the problem hidden inside the many-body self-energy. So let me stress a few concepts about this. So you have this self-energy, which bridges the free particles to the interacting system. So here you have a function, the green function of the non-interacting system, which has a very simple structure, and the poles are just the energies of the non-interacting system. But then you have, it is connected to the full interacting green function via the Dyson equation, where you have the self-energy. And the key aspect is that the self-energy, you see, is frequency dependent. This implies that the number of poles of the fully interacting green function is much higher than the number of poles of the non-interacting green function. And what it is done usually, or at least it is done as a first step, is to replace the fully dynamical self-energy with a self-energy evaluated at a specific energy. It can be 0 if you do a static approximation, or it can be the energy of a quasi-particle pole in what is called the quasi-particle approximation. Now, in this approximation, let's say one of the assumptions is that you can well describe the full interacting green function with a number of poles which is equal to the number of poles of the non-interacting system. In a few slides, we will see in practice how this works. But it is important that now you are replacing your free particles with some particles which are called quasi-particles, which are still not interacting at this level, but still which contains the effect of the interaction with all the other particles through this effective self-energy. Of course, through particles are interacting, and also the quasi-particles, they are in practice interacting, but let's say the residual interaction is much weaker, and it is related to the fact that the self-energy is dynamical in a sense, and the fact that in practice one would expect a much higher number of poles in the interacting system. So let me do a comparison in between our density functional theory, which you have seen in the previous lectures, and many-body perturbation theory, let's say, describe a system of interacting particles. So you have seen already that in DFT, this system of interacting particle is, let's say, mapped into a Kohn-Sham system of non-interacting particles. And then the price you pay is that you have this exchange correlation potential, which is local in space and is static. And still you have an exact representation in DFT, but by exact, I mean that you can compute some properties of the system, and in particular the density, in an exact manner. In many-body perturbation theory, this interacting system is mapped into another, let's say, exact representation of weakly interacting quasi-particles. And the price to pay is this time that you have a self-energy, which at variance with the exchange correlation potential is not local in space, and it is dynamical. But the gain compared to density functional theory is that not only you have the exact density of the system, indeed you have the exact green function and density matrix, but then you can also have the exact excitation spectrum of the system. So you have probably seen in previous lectures the Konesham energies are not physical properties, in principle are just mathematical objects. Instead, the quasi-particle energies, which you obtain within many-body perturbation theory, are physical properties which can be measured. Now, the key idea behind what is called the ab initio many-body perturbation theory, and then what it is implemented in the Yambo code, is somehow to merge these two aspects. So to merge density functional theory and atomistic calculation with all the diagrammatics of many-body perturbation theory. And this is done in two steps. So you first perform a standard density functional theory calculation, where you obtain your Konesham wave functions and Konesham energies. And then you use this information to build your reference green function, the zero-order green function. And then on top of this, you do diagrammatics and you insert the effects of the many-body self-energy. So you standard many-body perturbation theory, as I said, you have three particles. You map them in quasi-particles via self-energy, and then eventually you add the effect of the dynamical term of the self-energy. In ab initio many-body perturbation theory, you simply replace your non-interacting system with the Konesham system. And then, of course, you have to avoid double counting exchange correlation effects, which are inside the DFT potential, and then you have to subtract it in the first step. So just an example on what you get in a material, then again in the next presentation you will see that more in details. So this is the band structure of hexagonal boron nitride. And in black, the black lines you see, they are the Konesham energies, which, as I said, in principle, they are just mathematical objects. In practice, they are often used to describe the band structure, so the photoemission spectra of a material. And here you see what happens if you, on top of this, you add the effects of the self-energy in general. So you get a correction to the band structure, so the violet lines and the dots are a result of what is called the GW calculation. And you see that the first effect is an opening of the band gap, so the distance between the valence and the conduction band in the GW band is bigger than in the DFT case, and also a stretching of the band. So here you see that the GW valence band is more stretched compared to the DFT one. So let me remark another important aspect. Now imagine that you fix a K point, and then you want to plot as a function of energy your green function. Now the Konesham green function is simply this object, so it's something which has a pole at the Konesham energy. Instead, when you do many-body perturbation theory and you add a self-energy, which indeed is dynamical, there is a shift in the position of the peak, and indeed it is this shift, but there is also a broadening of the peak and eventually the appearance of satellites. Okay, this is, I mean, everything about the calculation of quasi-particle properties for this slide. I just want to also stress a bit about the performances of the code. So with Yambo, you can compute quasi-particle properties, and in particular within what is called the GW approach. And in the last, I would say 6-7 years, there have been a very strong effort in making this implementation very efficient. So here you see a comparison of the scaling of the Yambo code on as a function of the number of nodes on two different clusters. And in particular, on the left, you see a calculation where you run on standard CPU. So it's a cluster which it has, let's say, nodes with a standard Intel cores, 48 Intel cores per node. And the code is compiled with the Intel compiler. And then here you see the scaling of different what are called run levels, so different part of the code which compute, for example, the dipole, the screening, the self-energy, and other parts of the code. And at this level, the parallelization is done with MPI plus OpenMP. And then on the right, you see the same kind of analysis, but on a cluster which has NVIDIA GPU cards. And so this time, the the computation is done taking advantage of the CUDA-Fortran implementation in the Yambo code and with the NVIDIA compiler. And as you see from the timing, there is a significant speed up at, let's say, comparing the run without GPUs. I'm not going into the details. Just to mention that let's say, the largest run here was done on 1400 GPUs about, which is already let's say, a very significant performance. It's using, let's say, a number of nodes which is equivalent to 14 petaflops. And these were simulations which were about 1 year ago, and the last simulation done on the Cineca computer centers, which we are going to use, have been able to even reach 0.1 exaflop, which is even larger, let's say, performance. Okay, I think I'm running out of time, so I just want to stress that in a standard GW calculation, as you can see from this performances test, most of the time is spent in computing the response function. So here you see that most of the time here is due to this part of the code, which is actually the independent particle of the response function, which is needed to compute the screened interaction. So the effect of screening and of the screen interaction is one of the key ingredients which is important to compute many body perturbation theory properties. And okay, I think I will skip this part just to mention that with Yambo you can say also solve what is called the Bethe-Salpeter equation, which describes what happens when you excite one electron from the valence to the conduction band, and you have this electron and hole interacting, and there is the formation of an exciton. And that this, let's say, the GW plus the Bethe-Salpeter scheme is a standard approach to get the excitation spectra of a system with including both charged excitation, which you can measure in photoemission, and neutral excitation, which you can measure in optical spectra. And with this, I think I will conclude, and I want to thank you for your attention and acknowledge again the funding which Yambo is receiving from the Max project, which is enabling having Yambo ports on the supercomputers.
Okay. Okay, so good morning, everybody. I'm Alberto Guandalini. I'm a postdoc at University La Sapienza of Rome, and actually speaking from Osaka because I'm doing a visiting, so it's afternoon here. And today I'm gonna introduce you some more details about the GW approximation, and in particular which are the common approximations employed and some practical advices and about how to converge a GW calculation with Yambo. So in the first part, I will talk a little bit about the physics of excited states. So those experiments were to probe the excited state properties of systems. Then I will summarize a little bit and say a little bit about many-body perturbation theory and how to obtain the GW approximation. Then I will discuss about numerics and which are the equations implemented in Yambo. And finally, I will show a couple of very recent advancements of new algorithms which are implemented within the Yambo code in the last couple of years. So there are several experiments which are able to probe excited state properties of materials. And here I show a couple of examples, where direct and inverse photoemission spectroscopy. In the first case, we have light as an input to the sample, and then electrons are ejected with a certain energy, and it's the energy of the ejected electron and eventually also their momentum are collected by the detector. And in this case, we are able to probe the the valence states, as I will show in a moment, while in inverse photoemission experiments, the opposite happens. So electrons are ejected to the sample, and what is measured is the light coming out from the sample. There are other examples like optical absorption. When it is measured, the light transmitted through the sample, or for example, in an electron energy loss spectroscopy, there are electrons which are again injected to the sample, and what is measured here is the energy lost by the electrons and how they are deflected. So we can split those experiments in two categories. In the first one, we probe charged excitations, and this is because the number of electrons in the system is changed during the measurement, while neutral excitations for these other kind of experiments where the number of electrons does not change. So talking a little bit more in detail about photoemission, we have lights coming in which excite one electron from valence band to a vacuum state, and then using energy conservation and the frequency of the incoming photon and the kinetic energy of the outcoming electron, it can be seen here that we can have we can describe the difference of an excited state of n-1 particles and the ground state of an n-particle system. Thus, we have a fingerprint of valence occupied states, while in inverse photoemission spectroscopy, the opposite happens. So we inject an electron to a conduction band, then some light is emitted, and again, using conservation energy, we can have some information about the unoccupied conduction states. So here I show an example of angle-resolved photoemission spectroscopy, where also the momentum of the ejected electron is measured, and it can be seen here for graphene that we have a fingerprint of the bands of graphene with the Dirac cone at the K point and, for example, the band gap at M. So talking instead about optical absorption, we have the famous Beer-Lambert law, and the exponent of this in this law is proportional to the imaginary part of the macroscopic epsilon. And as the excited electron does not move far away from the sample, we have a neutral excitation, and in general, the electron can interact with the hole it left behind. And it can be seen here in this example of lithium fluoride, where we have an absorption spectrum. The experimental one is with black dots, and it can be seen that without including this electron-hole interaction, we don't have even a qualitative agreement with experiments, while electron-hole interaction is really important in order to reach some comparison with experiments. Thus, we can distinguish, again, within two different kinds of excitations, charged excitations, and one fundamental quantity here is the fundamental gap, and neutral excitations, where one fundamental quantity of interest is the optical gap. And as already Davide said, with many body perturbation theory, we have two different strategies. So for charged excitation, the GW approximation, and for neutral excitation, the solution of the Bethe-Salpeter equation. And in this talk, I will focus about the GW approximation, so charged excitation. But before doing that, it's important to see how density functional theory performs in the calculation of the fundamental gap. Well, in principle, the fundamental gap can be defined in this way as an energy difference, an energy combination between the ground state energy at n-1, n, and n+1. So as the fundamental gap can be expressed as a difference of ground state energies, in principle, it can be exactly computed with the exact density functional theory in this way. But of course, in practice, you need to resort on approximations. And what happens for finite systems is that local and semi-local functional seems to work quite well. For example, here I show in the x axis the experimental ionization potential, while in the y-axis the calculated ionization potential, and you can see here the match between theory and experiment is quite acceptable, while the situation is different for a solid. And this is because to add an electron to a solid is something more delicate, because this means to add an infinitesimal fraction of it to each of the unit cell of the system. And if you do this for a local or semi-local functional, you obtain that the fundamental gap is equal to the Kohn-Sham gap, while the Kohn-Sham gap is not an accurate value to get the fundamental gap with respect to experiments. So this is why usually many-body perturbation theory is employed in order to get the proper fundamental gap of solids. But here it's important to have a note. So there are advanced functionals in the literature which are able to reproduce the fundamental gap, but this is still a matter of research, and usually they take more computational time than density functional theory with a local or semi-local functional. So there are alternative strategies with respect to the one I'm going to show you today, but this possibility will not be covered in this lecture. So let's now move more on many-body perturbation theory. As already Davide said, so the main quantity here is the one-particle Green function that contains the information about the electron or Hall propagation from one point in space-time to the other. And we can understand this by using the Lima representation in this way, and we can see that the poles of the one-particle Green function are exactly equal to the difference between an excited state of the n plus or minus 1 electron system minus the ground state of the n electron system. And this is exactly what we call bands in an interacting system. And so the goal of Yambo GW calculation is exactly to find the poles of the one-particle interacting Green function. Then in order to construct a many-body perturbation theory, we need a bare Hamiltonian and a perturbation. And what we do is to take the Kohn-Sham as the bare Hamiltonian, and the difference between the Coulomb interaction and the Kohn-Sham potential, the R3 Kohn-Sham potential, as the perturbation. Then we define a non-interacting Green's function, which actually is the Kohn-Sham one. So I would think that the non-interacting Green function is the Kohn-Sham one, so constructed with energies and wave function from a density functional theory calculation. And then we can use the infinite resummation, Feynman diagrams, and all the machinery of many-body perturbation theory to have obtain a Dyson equation for the interacting Green function in terms of the non-interacting one and the self-energy. So from a Feynman, let's say a Feynman diagram point of view, what happens is that in your interacting Green function, you start having, so you create an electron or a hole, and while it is propagating with non-interacting propagators, also scattering events happens, and you include the physics by including these scattering terms through the self-energy contribution and by solving the Dyson equation. Here just a slide to explain, try to explain in the quasi-particle concept. So as you have seen, the added electron experience some scattering events while it is propagating through the solid by interacting with the other electrons. And these can be seen like, in this case, an added hole that produces an electron cloud around it, while the poles of the interacting G are propagating freely. So we can think about the quasi-particle as the hole itself and its electron cloud, which propagates freely around the solid. And in this example here, it is like the added electron or added hole is like a boat, while it is traveling through the sea, and the sea are the electrons of the solid. You are going to have some sea waves, and your quasi-particle is not just the boat, but the boat plus the sea waves, which are traveling through your solid. And before going on, it is also important to define what is called the screened interaction. That is one of the main quantity in a GW calculation. And this is defined when you add a charged, so a trial charged particle as the Coulomb interaction plus the R3 interaction of the induced charge density. So you have a probe charge. This probe charge not only has a Coulomb potential, but it also induces to the solid an induced density, and this induced density itself produces a R3 potential. And this is a quantity used to describe an effective interaction between two charges within a solid. Well, this interaction is mediated by the solid itself. Here there are the equation in how to compute it, but in a subsequent slide I will show and explain them better. So here show the Hedin's equations. This is a set of 5 self-consistent equations, which formally solves the many-body perturbation theory at infinite order. And it's important to note here that this perturbation theory is done not with respect to the Coulomb interaction, but with respect to the screened one. This is because the screened interaction is less intense than the Coulomb one, and then again, perturbation theory works better if the perturbation is of low intensity. So of course, as usually happens, it is not possible to solve the problem exactly. We have to resort to approximation. What it is usually done is to do the so-called vertex approximation. So you remove the many-body contributions came from the vertex corrections, and you end up with a self-energy that is given by the product of the green function times the screened interaction, and this is why GW approximation. While the screened interaction is computed within the random phase approximation. So what it is usually done next is also not to compute all these equations self-consistently, and this will give us the G0, W0 approximation, but just compute them. So use for the self-energy the Kohn-Sham green function and the screening computed with, again, Kohn-Sham Green's function. So the screening computed at the DFT level. The only equation that is solved self-consistently is the equation for the one-particle green function. So actually what Yambo does in a GW calculation is to solve this equation here. Of course, equation 4 is trivially solved. So what I'm going to do for the rest of the talk is to express this equation in a more concrete way in order to provide some hints about the convergence parameters and also so what is going on with them in more detail. But as a starting point, let's talk about the basis set representation, because in order to describe numerically an operator, we need a basis set in order to have matrices which represent an operator. And in Yambo, there are actually 2 basis sets to describe the Hilbert space. The first one is plane waves, exactly as in quantum espresso. Then you have a convergence parameter that is a cut, so the energy of the maximum plane wave. And but we have also Kohn-Sham states. So another conversion parameter is the number of bands, of quantum bands included in the calculation. And the reason why we have two basis sets in the Yambo code is that the different operators are more efficiently described with a different basis set. In this case, Yambo computes in plane waves the screening, while the one particle green function has self-energy in the basis of quantum states. And this is because the quantum green function is diagonal in the basis of quantum states, and also the self-energy, we are going to consider it diagonal, even if this is an approximation. Of course, we have these quantities here, which are can be computationally demanding to compute, that pass from one Hilbert space to the other. And here it is also important to note that these two parameters, so the number of bands and E cut, are interconnected. And this is because as we move from one Hilbert space to described in one way to the other, if you enlarge, for example, the number of plane waves, you are considering a higher Hilbert space, and then you need, of course, to consider this higher Hilbert space in the basis of quantum states. So how to solve the Dyson equation? Actually, the Dyson equation can be formulated in a nonlinear eigenvalue problem with the quantum Hamiltonian and the self-energy, where the eigenvalues will be the quasi-particle energies and the eigenvectors, the quasi-particle orbitals. And what it is usually done here is to do the orbital approximation, so to consider that many-body perturbation theory does not change the orbitals with respect to DFT, so that DFT orbitals are already a good starting point. And then we end up with a self-consistent equation where we need to evaluate the self-energy already at the quasi-particle energy. So what it is you've done now is to tailor expand the energy dependence of the self-energy around the quantum energy. Then we end up with this expression that is no more self-consistent, where these zeta factors include, of course, the first-order derivative of the self-energy with respect to energy. So in practice, this is computed with finite differences. Then we end up with the quasi-particle energies that are the quantum energies plus a quasi-particle correction. And in order to compute it, we need to compute the self-energy at two different energies. The first one is the quantum energy, and the second one is at the quantum energy plus a little shift. So in order to compute the self-energy, we need to compute the screening. And in order to compute the screening, we first need to compute the irreducible polarizability, which describes electron hole excitations not interacting one to the other. Here we have the plane wave representation of the irreducible polarizability. I'm not comment too much on that. Then we need to solve a Dyson equation for the reducible polarizability in order to have all the summation of the geometric series of the polarization bubbles. And this is done with a matrix inversion in G space. Then we have access to the inverse dielectric function, and with the inverse dielectric function to the screened interaction. Because the screened interaction can be also viewed as the Coulomb interaction mediated through the response, the dielectric response of the system. So this is often the most time-consuming part of the computation of screening. And this is because we need for each GG prime matrix element, we need to do a summation over bands and an integration over the Brillouin zone. And then we have to do also an inversion matrix. And it can be seen here that we need to converge the GG prime space with respect to ECAT and the summation over bands with respect to the number of bands in the calculation. And to cut the number of bands in the Consham representation means to provide only a finite channels of excitation for the bubble diagram to the system. Then, of course, we need to have a Brillouin zone sampling sufficiently dense to converge the integral over the Brillouin zone. So with the screening, we can now compute the self-energy, and the self-energy is described with this Feynman diagram here. So we have an incoming electron with labeled by band index n and momentum k that scatter with itself through the screened interaction, which brings some momentum q and energy omega, while the electron passes through an intermediate state m. So due to Feynman diagram's rule, we need to integrate within all intermediate states. Thus, we will have an integral over energy, an integral over momentum, and a sum over the intermediate states. Then the non-interacting green function is diagonal in the Consham space, while we need to move the screened interaction from the plane wave to the Consham space with the matrix of change basis. So as the screened interaction can be seen as the Coulomb interaction plus a correlation part, and the self-energy is linear with respect to W, we can also split the self-energy into two terms. The first one is called the exchange term, because it is exactly the Fock exchange term, while the correlation part is the one which arises from the correlation part of the screening. As the Coulomb interaction is not energy dependent, the energy integral can be done analytically in the exchange part, while for the case of the correlation part, in order to avoid the calculation of the screening in hundreds of several energies, it is commonly employed the plasmon pole approximation. And in the plasmon pole approximation, it is supposed that the main response of the system came by its plasmon. Thus, we have an ansatz for its energy dependence, and we can also, in this case, compute analytically the integral over energy and arrive to expressions like this way, where we have, in particular, in the correlation part, the plasmon residue and the plasmon energy. We can see that as both of these two parameters depends on Q, we are including the physics of the plasmon dispersion within this model. So again, we have summations over reciprocal lattice vectors, which should be converged with respect to a cut, and a sum over bands here which represent the band of the intermediate state, which should be converged with respect to the number of bands. And these represent the fact that we are considering only a finite channel of this intermediate state. Then again, we need to converge the integral over momentum transfer with a sufficiently dense K-grid. So here I show a schematic view of all the equations which are solved within Yambo, just to have a summary of the procedure. So first we start from a DFT calculation, which provides us density functional theory energies and wave functions. Then we can have easily the Consham one particle green function. And the first step is to compute the screening in plane waves, then to compute the self-energy at two different energies in order to have the quasi-particle correction and correct our bands in order to include many body effects. So here some results, and it can be seen that the GW, which are light blue dots, improves for what concerns the fundamental gap with respect to LDA in a large variety of solids. And this is because we explicitly added the physics of one electron and a removal through the use of the one particle Green function. So in the final part of the talk, I will briefly talk about some recent advances which has done in the last couple of years. And I start by talking about GW in 2D materials. Well, what it is usually done, for example, in quantum espresso, to treat 2D materials, this is an example for MOS2, is to add a sufficiently high amount of vacuum between the slabs in order to make them not interacting. But this will be more difficult for the case of GW because the Coulomb interaction is a really long-range one. So what it is done into the code is, instead of using the bare Coulomb interaction, we have a truncated Coulomb interaction. So we add a heavy-sided theta to let each electron interact only with the electrons plus or minus 1/2 of the dimension of the unit cell in the non-periodic direction. In this way, for example, these two electrons here are no more. So one electron is not, for example, interacting with its copy. And in order to, so the Fourier representation of the truncated Coulomb interaction is here. And it can be seen, for example, by looking at the long wavelength limit, that we have a different qualitative behavior with respect to the 3D case, which also gives us different features for 2D systems with respect to than the 3D one. For example, here I show that the convergence of the fundamental gap of monolayers like MOS2, HBN, and phosphorine is very slow with respect to the K-grid. For example, the MOS2 density functional theory properties are already converged with the 12x12 grid. And the problem of this convergence originates from the fact that the macroscopic component of the inverse dielectric function of a 2D system is sharp in the long wavelength limit. And this does not happen, for example, for a 3D material. And this is why we have this convergence problem. So what we have done is actually to compute the integral in momentum transfer in the correlation part of the self-energy with a more advanced algorithm that we call W average. So instead of just using the trapezoidal rule, so define a numerical grid and sum between the points of the grid, we now use the average of the screened interaction within its numerical domain, for example, in these hexagons here. And this is done by a combination of an interpolation scheme plus a Monte Carlo technique. So to compute the averages. And in this way, it can be seen here in orange that the convergence is greatly accelerated. And we are able to obtain convergent results with grid comparable to those of density functional theory. So something also which has been developed recently is to go beyond the plasmon pole approximation with the so-called multipole approximation. Here it can be seen, for example, the imaginary part of the screened interaction that is proportional to the imaginary part of epsilon minus 1, thus to the Hills spectrum. And it can be seen in black for the case of graphene that we have the pi plasmon, the pi plus sigma plasmon, and an onset of excitations at low energies. And of course, this rich physics cannot appropriately described with the plasmon pole approximation, which is in blue here, even if the plasmon pole approximation is somewhat able to find a plasmon between the pi and pi plus sigma plasmon. This is still remarkable. But but we can do definitely better by relaxing the single plasmon pole approximation by having an ansatz of multiple poles. And in this case, in red, we have 10 different poles, and we can interpolate also the energy dependence of the screen interaction. And it can be seen here that all the qualitative features of the imaginary part of the screen interaction are correctly described. So these two features, the W average and multiple approximation, have been implemented to the Yambo code, and we also implemented their combined use. And here, just to say that we use this to compute with an efficient yet accurate scheme the band structure of graphene, both near the Fermi level and for low-lying states. So to conclude, the GW method is able to accurately reproduce the charge excitation of a system, and charge excitations is measured, for example, from experiments like direct or inverse photoemission spectroscopy. There are many approximations involved, and here there is a summary like neglecting vertex effects, not solving the cell consistently within the self-energy, the quasi-particle orbital approximation, maybe the plasmon pole, or the Taylor expansion of the self-energy. There are also, of course, some convergence parameter. Here shows only some main convergence parameters like cutoff energy, like in quantum espresso, the number of Kohn-Sham states employed in the calculation, and the grid of the finite Brillouin zone sampling. And they also described some recent advancements, like this W average method that is able to speed up the convergence with respect to the Brillouin zone sampling, and the multiple approximation that is able to go, let's say, to describe the screened interaction with physics that contains more than one plasmon. So here are some references, and thank you for your attention.
So now we start the tutorial in which we will practice some GW calculations, as it was explained in the previous lectures. We will start from simply converting the DFT data from Quantum Espresso to a Yambo format. Then there will be a discussion about how to create and manage the Yambo input, then some runs. We will see some examples of convergence parameters. You have seen from Alberto's talk how important is having converged results for the various pieces of the self-energy. Finally, we will discuss also some parallel strategy, Yambo can run in parallel on GPU and CPU. We will see some examples of that. And in the end, we'll try to reproduce a halfway decent band structure for monolayer molybdenum disulfide. So this is the content of the tutorial. And now I just give the floor to Matteo that will walk you through the first half.
Okay, you should be able to see my screen. This is the page of the tutorial. I don't know if I didn't see the link, so maybe if you can just paste the link into the chat.
I will copy paste for this.
Okay, thank you. So as Fulvio said, I'm Matteo. I'll walk you through the first part of the tutorial. And right before we begin, I will ask you to log in into Leonardo. And please remember to move in your Scratch directory, which you can access with the environment variable. We do not want to run on the home directory. So once we're here, we move to or create a directory for the Yambo tutorial. And so right before we begin, I will ask you to download the tutorial files we need, because this will take a minute. In the meantime, we will see some of the stuff we already seen and discuss the tutorial. Okay, so at the end we will get, sorry, there are some questions, or maybe, okay. So we at the end we will get a pseudo good band structure for molybdenum disulfide. So this we already seen before. So at the end we want to compute the quasi-particle energies with the so-called Newton method. And here we recognize some of the stuff we've seen before. So the DFT Concham wave functions, energies, the exchange correlation potential, and the main quantity we're interested. The main quantity we need to compute with Yambo, which is the self energy in the GW approximation. As we've seen in the talk by Alberto, this is divided in two parts: an exchange part and a correlation part, which somehow we can see that the general flow of the calculation we are going to perform. On one branch we have the easier exchange part of the self energy. On the other one we have the correlation part of the self energy, which needs, of course, the screening. Okay, so this is going pretty slow. I don't know why the expected time is 12 minutes. It's a bit of a bummer. Am I the only one trying having this problem with the download speed? I don't know. Giacomo, did you try?
I did it like half an hour ago. There were no problems.
Okay, so maybe the connection with the Leonardo.
No, maybe there's a lot of people connected.
Okay, so it's maybe due to a lot of us. Okay, yeah. should have done this before, maybe. I'm not sure if I have one already ready. No, I'm afraid not.
But so maybe we can tell the students to interrupt and then they can copy from your file.
Yes, I don't know, because we tried also with the copy and it wasn't fast. So because we were all on the login nodes, so I think it'll get plugged. But maybe we can try. So if you do Control-C, so to interrupt the download, see if this speeds up. Then I will move this tarball in the work directory, which everyone can access.
Yeah, exactly.
See if this works.
I mean, for the students, if you can interrupt the download, it's very slow. It's also pretty big.
Yeah, it's 1 gigabyte
1
actually.
gigabyte.
So yeah. No, in our test it took like a minute, but yeah, we didn't think about the number of people downloading it.
Okay,
So the file should be in the work folder now, right?
I don't know. Yes, there is one. Okay. So I interrupt mine.
Thank you, Apolinario, for having placed the file so fast.
Mhm. Okay, this also should take okay. Okay, so,
Okay, so for the students, they should be able to run this command, to copy from.
you can copy just with the same. Okay. Oh,
So can we put this command in place of the wget in the ACMD?
yes.
Fulvio, can you do that?
Mm.
Yeah, it will take some time. It's better to paste it in the chat, honestly.
Okay, yeah.
Don't have easy access to the chat, so if someone can do that.
Yeah, already done. Thanks, Martin.
Okay. Thank you. So we should have all our files. Okay. So looking at the flow of the, sorry for the inconvenience, looking at the flow of the entire calculation, the first thing we need to do is to convert the DFT data to databases that are readable by Yambo. To do that, we open an interactive session with this command. We ask for the account where we are allocated, and just one MPI task. And since we use the Yambo compilation on GPU, we also ask for GPU. Be aware that this will last 30 minutes only, which should be enough. Okay, so now that we run this command, we see that we have a job allocated to a user, and we are in a compute node here, as you can see. From here, the first thing we do to load Yambo, like so, and move to the first directory, which contains simply the saved directory generated in this case by a quantum espresso calculation. This you control with this is the prefix dot out there save direct. We go inside it and we recognize some of the usual quantum espresso data. Okay. And we run this command here, pty, which is that will translate essentially this data into Yambo databases. We can do that in the background. It should be fast. Okay, so as you can see here, we have a couple of new files. First of all, the saved directory, which contains all the databases, and a log file, which we can expect. We will do this a lot. Okay, where we can see what Yambo, what pty did in this calculation. And since we're here, we try to run this again. This command again to see how Yambo behaves in general when we run multiple calculations. Should be faster. We see that Yambo does not overwrite log files or rep files, instead generates new ones with an increasing number as a suffix. And most importantly, if we inspect the new it's clearer from the report. We'll see in a second. However, the databases we are now we are able to see which databases we generated. There are so-called the static databases, which will begin with NS. We are not done yet. What we do now is the initialization step, which simply from outside the save that directory, we run Yambo, and this will run a setup calculation, which maybe it's already done. Yes, it's already done. Again, we have a couple of new databases here, a new log file, a new report file, and most importantly, these two dynamic databases here that Yambo needs to run any kind of calculation. Okay, and again, if we run Yambo, if we look at the setup, this now contains a lot more information. We can recognize some of the parameters we used in the DFT calculation. For example, the first one is the number of states we included in the quantum espresso calculation. In this case, 300. The K points, the cutoff, and so on. And we also have access to a number of information concerning the energies. Most importantly, we use that we will use later the gap, the DFT gap, and its location. So in this case, we see that's between at K point number 7, between bands 13 and 14. Okay. Yeah, you can see here again a summary. If we run again, this is what I was trying to show you before. We look at the log file for the setup calculation here. We have a different, we have a bunch of lines, like the hash lines here. That means that Yambo is doing some computation. If we run again Yambo, the initialization step, we will see the behavior. Look at the new log file. There are no more hash lines because Yambo already found the databases and it's simply reading it. It's not computing again the stuff it needs. This is important. I will remind you also later in the convergence part, because if we want to actually do a proper convergence run, we should keep all the databases separated. Otherwise, Yambo will read always the same data and not compute new one. Okay, now we are ready to move the save directory into a more appropriate location. The save together with a report file which will be useful. So we're here and we move it in the 0101 directory, GW first run. We go there as well. And be aware that in all directories you will have a bunch of this ref, which is a copy of a save directory with the calculations already run, so you can check if your results are the same. The next important thing we need to learn is how to generate an input file. And the way that we suggest to do is using Yambo itself. With the -h flag, Yambo -h, and be aware that we can do this now on an HPC machine because we are in an interactive session. Okay. So with the Yambo -h, we can access all the flags that we need to pass to Yambo to generate our input file. Okay, so here we can see what we want to what we need to have in the input file. So we want to run a GW calculation. We also want to access the Coulomb potential truncation that we see in that Alberto showed us before in his presentation, because we have a 2D system. We also switch on some of the parameters for all the parameters concerning the parallel run, although this will become important in the next part. However, we can see, for example, here in this command, which is kind of obscure, we have a bunch of flags. We can enter these flags here and get some more information. For example, Yambo -h GW0 here, which stands for GW approximation. GW0. And here we can choose with an additional string the plasma pole approximation, which it's the one we want to use today. The next one is this -GN, -G here stands for Dyson. We can do that as well and see what options we have. Dyson. Okay, we want to choose here the N, the Newton method. And since we're here, and I will use this a lot, I will suggest you to do the same. So from the main Yambo website, you can access the Yambo wiki, and here right at the top we have the cheat sheets that are really useful for when you run Yambo calculation. So for example, we found we added that -n option, okay, minus Dyson n. We see that the n string means basically this that we've seen before. This way to solve the nonlinear equation, just approximating expanding the self energy around the constant eigenvalues. This will introduce the renormalization factors, all the stuff that we've seen before. So basically, that flag means we are going to use this approach. Finally, -B, -R, it's the Coulomb potential. This will switch on the variables for the Coulomb potential. The -V, capital V, it's used to switch on a set of variables. In this case, the one controlling parallelization. And the -F one, it's not an important one because we will always use this, is to choose the input file name. So to direct explicitly. So actually we are ready to run this command. Okay. Now we have the gw.in file. But before we get kicked out of the compute node, let's just exit. This will cancel our job, our interactive session, and we're back into login in the login node, back into the directory where we run srun from. So we go back into the GW first run. Okay. We have a new input, and now we can open it. Okay, make this slightly bigger. Okay, this can be a little bit overwhelming. However, we can help we can orientate ourselves in the input file, looking at the comments here. So first we have a block here with all these R flags here. These are run labels for the Yambo code. So first off, we see GW run label, plasma pole approximation. So all the stuff we recognize. Here we have a more explicit one is epsilon. I mean, if one can read can read it, it's epsilon to the -1 dynamic, which is none less that the screening we need to compute for the correlations part of the self-energy. Here, rim cut related to the Coulomb potential part, and each of these run levels gives us access to a bunch of input parameters. For example, here the Coulomb potential part switches on this block here. Okay. Now let me follow this part. Okay. So the first two important things we want to look at is are these two variables. Okay. We can go back to the cheat sheets and try to find the related cheat sheet. So this is the formula implemented for the exchange part of the self-energy. We see that we have a summation on only occupied bands, and the two variables that I have here highlighted are actually connected to these sum over reciprocal lattice vectors. Now, this very easily, as it's also written here, we do not change it. So thanks to the initialization run, the default values are set to the maximum available, which is determined by the cutoff used in the DFT calculation. Okay, and if possible, we want to leave it as that, so the maximum values, and we want to keep these two numbers here the same, because as we see here, eventually the exchange part of the self-energy and the exchange correlation part of the exchange correlation potential part from the DFT calculation will be subtracted from each other. So to have the same precision in this operation, we want to keep these two values the same. Okay. Okay, that should be all for the exchange part of self-energy. Now the second part is the correlation part. Again, for the correlation part, we know that we need to compute also the screening. Okay, so the first variables we see here are for the screening. So here, this block. Go back to the cheat sheet, and we find, okay, this is the quantity that we want to compute that includes the response function, which we can see here. It's a bit more cumbersome, I hope you see. However, we can recognize some of the stuff. So the kernel, in this case, we are using R3. Okay, so just this element. We have a summation, again, hidden. There's no related box here, but we can see it. We have a summation that goes on only on all the states. So valence state and conduction states. And this would be, this needs to be converged. Here is an additional variable that controls the summation of the reciprocal lattice vectors, so the response block size. Okay, And finally, more obscure one, which is this long DRXP, which essentially, when we take this limit for the screening, in general, we have to this limit can be considered along a general direction, and so we need to pay attention to if we are working, for example, with unknown isotropic material, we want to select carefully along which direction we want to take this limit, because in general we could have a different result. Okay. In our case, we will do that now. So if you are inside the input file, just do this now. We will put a generic direction, so not along one specific axis, for example. Okay. Another one that I see here just below is the plasma pole energy. We usually do not change it. Should be fine. Okay. I think I said everything about this. We have another block here, which is more it's related strictly to the correlation part of self-energy. Again, we go back into the cheat sheet and we try to identify it. Okay, it's here. So it's again a summation of overall states, included the empty ones, and this again needs convergence tests. Finally, we also see this G-term kind here, which is a tool that essentially speeds up the convergence with respect to this parameter. And if we have time in the tutorial, there is a dedicated part to see how this behaves. Again, the Dyson solver, we already saw when we generated the input. And another thing that we can control here with this QP K range is essentially the number of quasi-particle correction and the location of this quasi-particle correction that we want to compute. Okay, so this by default includes all the bands and all the K points, but this would be very long of a calculation, and we will modify according to our needs. For example, in the convergence part of the tutorial, we will focus on the gap, and from the report, we can see where, at what K point, and between which bands the band gap is located, and we'll set that accordingly. Okay, this is another important part. We go back up in the input file, and we set the parameters for the Coulomb potential part. Okay, so first off, we set the number of random Q points used for the random integration method. We set to 1 million. Let's see. Okay, this in general should be fine. Also, this one to around 100 residual lattice vectors. This in general, I mean, you can see if you want to see a different how it behaves, how the corrections and the quasi-particle correction change when we change the parameter. But in general, these numbers, these orders of magnitude here should be fine. And we choose our cut geometry for the Coulomb potential part. Again, this is, we can orientate ourselves in the cheat sheet. So this variable here sets a region S outside, which can be of a shape that a box or a cylinder and so on, outside which the Coulomb interaction will be set to 0, is to avoid interaction between replicas. We choose slab Z set because this is what we have in the DFT calculation. So the molybdenum disulfide layer is in the XY plane, and the vacuum is along Z. And we can ignore these other variables here because they are related to different cut geometries. Okay. This maybe it's more useful to comment in the parallel run. At this moment here, we just ignore because we leave to 0 and we don't specify any parallelization. The code will set it automatically according to the job submission. So just to do a recap here, we saw that we identified mainly three input variables that we need to converge. This summation here over all states, the response block sides. So this is both for the response function. The summation on all the states in the correlation part of the self-energy, but we are neglecting some as really important parameters. The first one is the K-point sampling of our system, of our Brillouin zone, which is set by the DFT calculation. So this is pretty tedious to do because we have to run multiple K-point, multiple DFT runs with different K-point, increasing some mesh sampling. Regenerate the databases, and calculations, of course, will get more and more heavy. So we'll ignore this part, but it's really important. And finally, which is specific to our case here, the vacuum separation, which is essentially the vacuum we have in our unit cell. This again requires multiple runs. If you notice here, this cut geometry that we chose will set a 20 Bohr value for the cut of the Coulomb interaction along Z. Where can we find this number? We can find it in the setup, because as we've seen before, we can go to the unit cell part of the report and see that the unit cell we are considering as indeed 20 Bohr as a lattice parameter along set. And this will be, you don't need to specify with the slab Z because it will take it directly from the crystal structure. Okay. We go back. We look at this again. If we forgot where the band gap is located, because for the first run we will simply run a calculation to get the quasi-particle band gap for this material. And we see that again, it's this is the DFT value, and it's between band number 13 and 14 at K.7. So we will set these values in the input file. Go back into it. So here 7, 7, 13, 14. And we also change a couple of other parameters just to have a fast calculation. No, here it should be all fine, the Coulomb part. Here we want to reduce this number of bands to 20. 20. This will lead to 1, I guess, yes. And also here it's at 20. Just to see what we get. Now, we are ready to run the first calculation. We just take a look at the job submission script. Here we will run on 2 nodes, on 2 GPUs, sorry, on 1 node. And again, this is the way Yambo is coded. We just choose as number of tasks as the number of GPUs we intend to use. Okay. Okay. Again, we see the module load part. And some other specifics here that are for Leonardo. But we also see that there are some additional flags here. Okay. Maybe we can go back if I still have it. Yes. In the Yambo -h, we have -j, so a job string, and a C flag, a communication directory. This is because, as we saw before, Yambo generates new databases for each run, and where the databases will be stored can be controlled via this flag here. If we don't specify it, they will all end up by default in the save directory. And this communication directory is where all output, report, and log files will be stored. We are ready to submit the job. Sorry, as batch. Run. Okay. Just remind you, if you submit it by accident, the input is not still ready, you can always ask cancel using the job ID in case you need it. Okay, still in the queue. Interesting. Yeah, who knows how long it will take to run. Yes, is also another NDCOM, and I have an alias here as Q, but you have also each one of you as a user environmental variable here. My name is my case is this one. Okay, I don't know if it started. No. Some of you also in the tutors have tried. It's already run.
So in my case, I'm not trying. But,
you're not okay. No, also from the students, if someone has some results, maybe I can. No, this is too much. Okay. Oh, okay, it's running. So maybe we can now take a look at. So in the out, we have again a log file and a directory with log files. So a report file and a directory with log files. This is a typical Yambo behavior when you run on multiple with multiple MPI tasks. So we will have as log files a number of log files equal to the number of MPI tasks. In this case, 2. This should be already done, but we can inspect the log file. Okay, we recognize that Yambo is doing is computing some quantities. The chi function. At the end, there will be the GW calculation itself, and then we also have these numbers here that separate the various run levels of the run level of the calculation. Indeed, if we remember these two ones, the first one is should be 7 here, dynamic dielectric matrix, okay, and the other one was 9 for the GW GW calculation itself. So we open the report of our calculation. We can go to number 7 of the index. 5, 6, 7. Again, this is the same exact string we find in the log files, and we see that the Yambo is generating a new database, ndb.pp, in of course the job directory we specified with the -J flag. This database then we expect it to be read somewhere. Indeed, in the GW part of the calculation, Yambo is reading this database to access the data it needs. We can also inspect the output file. Will contain some information on the input file, the parameters we used for the calculation, but the actual data is it's here. It's in these 2 lines here. So we computed just 2 quasi-particle corrections, and the results are in these columns here. So this is the DFT value. This is 0 because Yambo sets the 0 to the top valence to the highest occupated state, top of the valence band. And if we want the quasi-particle correction, we need to sum these 2 columns here. Okay. This I'm just telling you because we will find it in the job script for the convergence part. So with this command, okay, we can actually access so with grep -v, we just extract all we need, only all that does not match the dash. So we get rid of the comment lines in the output file. Okay, and again we need to sum these two columns. We do this with AWK. Okay, so we do this for the valence band. We do this for the conduction band. Yes, here, tail. And then, for example, using basic calculator, we do this minus, but this one is negative. We have the result, the gap of our the quasi-particle gap. Of course, this will be highly no, this won't be precise. We will see in the next part how to refine this result. No. Okay, if everything is okay, it's just to how to manage the input file, how to I mean we took a look to the most important parameters we want to discuss. We need to that we now will go to converge. We also saw how to extract the output, the results from the output. Again, as a reminder, it's important when you run when we will run the convergence part of the tutorial to specify at each step a different job directory. Otherwise, Yambo will use the databases that it's already computed. Okay. We move in the convergence directory. We have a bunch of files ready for us. We already run, from this we see that if we look into the save directory, we already have some dynamic databases. This means that some calculations were already done, so this folder here is prepared just for the convergence study we're going to do. But you have to make sure that the needed databases, these two, for example, coming from a setup calculations, are already present. Okay. I think we can inspect the input file. This one, I01 GW. Okay, recognize some of the parameters, and in this first step of the convergence part, we only want we only focus on the on these two variables here. That if you want, going back into the cheat sheets, are explicitly this summation and this summation. We already see from here that this is quite this can be quite cumbersome to do because the two parameters are not independent from each other. So we need to converge them simultaneously. We will see how we do that. Again, we only focus on the band. And we keep this other parameter that we will converge later to, let's say, a reasonable value. So we don't just put only the valence bands to make it fast. It's not a good idea. Okay, other things I see that are ready. Maybe we can, if the run 01, this is the first job we will submit. It should be, sorry, I didn't want to open it. It should be okay. So in the meantime, we will run it. We will submit the job. Okay, it's pending. So it starts eventually, but in the meantime, as I was saying, we can take a look at it and see what we're doing. So this part here is just for Slurm here. We load the Yambo, then we choose the input we just opened. We just looked at I01 GW as an origin file. We will modify it with sed command. And we see that we have a double loop, one on this variable here, and one on this other variable here. So these two, we see that at each step of the of the loop, we will change the values of these variables, making it bigger. Okay. So the SCD command just is pretty complicated string here, but essentially for this we are simply the line that starts with this line, we are removing it and replacing with the number that we want to use for the calculation. In this case, it will be 6 readbacks, 8 readbacks, 10 or 12. Okay. Each of these for a fixed value of bands included in the polarization function, in the response function. Again, if you want, you can see what this command does. Simply trying it in your terminal. And we also see, sorry if I repeat it again, that we generate each time a different input and specify different job directory and communication directory. So we have all separated. Now let's see, okay, it's running. If we look into the summary file, we have we're starting to get some values here. Is again all done automatically by the bash script here. So at the end of each calculation, we will grab our valence quasi-particle energy, conduction quasi-particle energy, and put it in this summary file, which is different for each set of for each value of polarization bands. So should still be running. You can also inspect, see what's happening in the log files. Okay. A bunch of them are already finished. Some of the others will be generated as soon as the calculation starts. Yeah, I guess we wait for a second for the job to finish. Should be almost done because we see that we have the summary for the 80 bands calculation. Okay, it's finished. Now we can use the plot 0, 1 to see our first results. Okay, there is a Python script which will at the end generate an image. To run it, we need to maybe a little bit hidden if you're lost in the tutorial, but make sure to load Python before running the command. Okay. We have a file that the easiest thing you can do is to copy it in your local machine. So you should specify, I think, your user and the login part. These are the same as when you connect to Leonardo. I have an alias here that manages stuff. Okay, copy the path of the file, not SSH, but SCP. Let me see. Yes, I have already the image. Okay, it's the same as reported here in our file in the tutorial. So we basically at this point we are ready to move on to the remaining parameter we need to converge. Before we do that, we just select two values for the number of bands in the response function and the response block size to a converged value. In this case, will be 80 bands. And 10 Rydbergs should be fine because we are under 10 millielectron volts of error. So assume it's converged. Again, this is all neglecting the K-point sampling of the Brillo and so on. So to do that, we copy the input that contains 80 bands as variables and 10 Rydbergs into a new origin file that we use for a second script. Okay. If we open 02 GW, we have 80 bands here, 10 Rydbergs here, and now we will need to modify this. To do that, we have a second bash script, 02, which we can actually, let me do that now, submit. So in the meantime, it comes. Okay, so in this case here, we again we are choosing our I02GW as an origin file. We have a new we will have a new summary file with the quasi-particle corrections, a new set of flags for the calculation. And essentially these values here that we will loop on as number of bands. Again, well, if you want, go back to the cheat sheet. We are changing this parameter here. Let's see how it's doing. Still in the queue.
don't know if in the meanwhile there are questions.
Yes,
That
sorry.
has not been clear. Curiosities. If you need maybe a recap of what has been done up to now.
This point, sorry, just I'll check if. Okay, no, the calculation is done, but okay, yes, now it's done. So if everything is clear, we can see our next plot using the plot 02 script. We have a figure 2. You copy on your local machine and okay. Here we have the convergence with respect to the number of bands. We see that this is pretty slow. Okay, so again, here you have a spoiler of what we are going to get using the terminator. Opening this box here, we should have time, I think, with the I don't know, Fulvio, how I'm going. What do you think?
No, you have time. Yeah,
Okay.
do go on.
Okay. So as I mentioned before, there are some tools in Yambo that can be used with the gterm kind variable that speed up the convergence with respect to the to empty states included in the calculation. Now we run this command here. This will switch on the terminal. If you want to, I mean, look at what this is doing. So here we have this variable here which is set to none. We will choose the so-called Brune-Malgonze terminator and paste it in a new. This will be a new origin file. IC02 GWBG. Okay. Now we have the terminator switch on. Okay. We also duplicate our job, our script, and modify it accordingly. Now here we should be careful. So first off, we want to specify BG. The summary will be 7503BG. We keep the same numbers to again have a nice comparison. Label, we will change hunting BG, and input, of course, BG. This should be all. Let's see. We can 03. Again, it could be. Okay, this is starting now. G-bands. It's a bit strange. First calculation should be done. Not. See what's happening in the log files. Out G 20 bands PG log number 1. No, okay, it's run. It's done. I don't know why. Okay, now we have 2, of course. Since we already see that we are well below the numbers we were obtaining before, because in the first in the plot you obtained before, we were around for the first 3 calculations. We were above 4.20. Okay, now below. In the meantime, maybe we can enter the plot 02 and comment this line, uncomment line before, to include also the other file, the other summary file. Okay. The calculation is done, it looks like, yes. We run again the plot script. I think we should have overwritten this file here. Yes. Okay. Nothing new. We already saw that before. We are converging faster with respect to the sum with respect to the number of bands. So the take-home message: use the terminator in your calculations. And I should also have time to do this other part. This is pretty interesting. So as we know, we are using a really coarse grid for our calculation, just a 6x6 k-point grid. So what we can do now is use the RINW accelerator here and see what we get. First thing we do is to duplicate our suitable input file, this one. We won't use the terminator. So let's do that and open I04GW file. Again, the parameters we used before, 80 bands, and read works here. No terminator. But what we do is we add these 2 lines here. Anywhere is fine, actually, in the input, but just for convenience, we will do that here, just at the end of the run level. Okay. So we have a new, if you want, a new run level here, the rim W, and an associated variable which we set to 15 number of reciprocal lattice vectors. Okay. Again, this should be fine. We copy the convergence script, and we modify it. Now here, again, be careful when you do when you modify your file. So we will not use this one, so don't worry, because we will just modify the label below. We want to update the summary file to rim W. G-bands, we will remove the loop. We leave it to 80 number of bands, because this is what we have in the input file. The label, we add G-bands rim W. Also the input file, rim W. And finally, this should be the same.
I think also the sed command maybe should be removed.
Yes. Thanks, Fulvio. I was going to break the tutorial.
Oh, by the way, there is a pre-edited file in the ref directory, so.
Yes, if you want to. Okay, now it should be the same. In general, if something like this happens, so you forget to update the label, and so you are you're doing a bunch of calculation, you can. I'm not saying that's easy, because if you look, we have accumulated a big number of files, but with the in principle, it's always possible to go some steps behind and redo some calculations. If you're having problems on that, just tell us. Okay. Seems that's already done. No, I won't do that. Unless summary 0. Okay. So I have the results, but since we are done with this part, maybe I don't know if Yonglei plans to do like a break before the next part of the tutorial.
We can have a break.
Okay, so when we come back from the maybe you can paste it in the chat if you have done it. The result which is in the summary 04, to see what bandgap we got with the rim W and where it's placed. So in a few seconds we can see from this data here, that's the same data that Alberto was showing before, It's from his paper. With the 6x6 grid that we were using, we're off the chart, essentially. Indeed, we got, even with the terminator, we got like a 4 electron volt band gap. Okay, let's see where we are placed with Dream W. This it won't be this point here, of course, because we used different parameters, a different number of bands, a different number of other convergence parameters.
Anyway, now we are going to leave convergence behind, at least for now, and instead focus on parallel running jobs in parallel. So let's go directly to the 03 GW parallel directory, and just in the interest of time, let's immediately run this script, job parallel.sh as patch. Let it go, since if we get stuck into priority and pending and stuff like that, we don't want to waste too much time. So now this will do its thing, and we discuss in the meantime. So for this new section of the tutorial, you see we have a save file, save directory. This is not the same as before. This is a much heavier system. So we rerun the Quantum Espresso DFT calculation, and this time we increased a lot. Well, we doubled the K-point grid. We are now running on 12 times 12, and also we turned spin orbit coupling on in this case, while before it was off, just in the interest of time. And you can see this here in the Yambo input. I can open also on this side, but I guess it's much clearer if you look on the right. In the quasi-particle correction range variable, we are now correcting basically all the Brillouin zone. So we are correcting K points from 1 to 19. And this is the number of K points in the irreducible part of the Brillouin zone, if you're using a 12 times 12 grid. And we are correcting bands from 23 to 30. If you remember before, from the calculation from before, the top valence band was the number 13, and the bottom conduction was the number 14. Now, instead, we have double that number. Now the top valence band will be the 26. This is because we are doing a non-collinear spin orbit calculation. So we are now have spinorial wave function and double the number of states explicitly treated by the code. So now 23 to 26 will be valence bands, will be 3 valence bands, and then 27 to 30 will be 3 conduction bands that we want to convert to calculate here. So these are all the matrix elements of the self-energy operators that we want to compute. And you've seen here, we also changed a little bit also the other variables. Now we are including 300 bands straight. This is the total number of bands from the DFT calculation. And also for the G vectors of the screening, we have 1 Rydberg. Keep in mind, so you can specify the cutoff of the G vectors in different ways, right? You can specify them by the number of reciprocal lattice vectors that you want to explicitly include. And then here you would write RL, reciprocal lattice. So before it was 1 RL in the previous calculations. Now it's 1 Rydberg. It's not the same number of reciprocal lattice vectors. Now we have all the G vectors that are included in a sphere of radius G, modulus of G squared, equal to 1 Rydberg in energy units. So we have more than 1 reciprocal lattice vector. It's easy to get confused by this. My suggestion is always use energy units for the G vector cutoffs that are also more general and can be applied to different systems, while instead reciprocal lattice vectors depend more on the details of your calculations. Okay, so you will see also if we open the input that we have totally removed the variables that are related to the parallel setup of the code. If I write parallel here, I cannot find anything. That's because we have included those in the submission script. If we open the submission script, we can go here. You see basically we append these variables to the input file. And now it's a good time to discuss them, right? While the job is running. So you see we have three different quantities that we are computing. The first, DIP, it stands for dipoles. These are the screening matrix elements. If you remember the lecture by Alberto from before, are these raw elements that allow you to pass from the plane wave basis to the Constant basis, right? These are calculated by Yambo and stored in a binary file. And since they have to be calculated for K points and transitions between valence and conduction bands, or actually also between valence and valence bands and conduction bands, Yambo allows for parallelization over these three channels. Parallelization over K points, over empty bands, C conduction, over occupied bands, valence. And so these are the roles. And then the variable above, CPU, is how we are assigning these roles. In particular, we are putting all our MPI tasks on the C label, which is we are parallelizing this calculation over empty states only, okay? Then we have a similar set of parallel variables for the calculation of the response function chi, that is the screening, right? You see the screening as momentum transfer vectors Q, G vectors, K vectors, empty and occupied states. So we can parallelize over all these channels. Of course, some will be more efficient and some not. We will discuss some of the basics of how to decide this. But so far, we just put everything again on empty states. And finally, we have a third set of variables. For SE, it stands for self-energy, right? And also here we have some channels, so still Q points, bands, and this QP, and we are parallelizing over QP only. What's QP? It's the number of quasi-particle corrections. So if we go back to the input, you see here we have 19 K points times 7, actually 8 bands. So the number of QP will be 19 times 8, which is 152. So we have 152, let's say, channels for parallelizing here. In principle, if we should not put here a number that is larger than this, right? But anyway, we are putting a low number now. Okay, so we are running these calculations on GPUs, not CPUs. So we are running on accelerators because the Leonardo booster, the machine we're running on, is a GPU machine, and now most, I mean, at least in Europe, most new high-performance computing facilities run on GPUs. And so Yambo is compiled with GPU support. How does it work, the GPU parallelization in Yambo? Well, basically, you have one MPI task per GPU card, as you can see here. So n tasks equal number of available GPU cards. So in a node, in a Leonardo node, you have 4 GPUs per node. So we will have maximum 4 MPI tasks per node, right? And if we check here in the job parallel, the submission script, you can see this here. So this we are running on one node. We are running 4 MPI tasks, and we are reserving 4 GPUs, okay? Now, here we are only talking about MPI tasks. There is also OpenMP, shared memory parallelization, which typically we call tasks, the MPI channels, and threads, the OpenMP channels. OpenMP parallelization is not extremely relevant if we are running on GPU, because the threads only apply for the small parts of the code that are still run on CPUs. So it will be very relevant if you run your full calculation on CPUs only, and we will see an example later. But so far, let's just keep going here on our GPU calculation. So this one that we just submitted, let's see how it's going here. So in my case, it's running. It will take more or less 10 minutes, so it's most over, let's say, was run, as I said, on one node and using all the GPUs available for that node, that is 4. Now, what we can do is also modify our script in order to run over multiple nodes. And then we will compare the efficiency, how the code scales. So we can run our largest calculation for this tutorial by modifying the number of nodes to 4. So now this means that we are going to run on a total of 16 GPU cards for a total of 16 MPI tasks, right? So, oops. So let me just submit this one. And also, so we did 1 node, 4 nodes. We also do 2 nodes to have some kind of an in-between comparison. If we do 2 nodes like this, then we are running on 8 GPU cards, 8 MPI tasks, right? So I start also this one. Perfect. If we check in our directory, you can see that we already have some output directories. These 2 ones, MPI1, MPI2, were already provided. This is where we use only 1 GPU, only 2 GPUs. It takes too long, so it's like pre-computed, right? While this MPI4 is the one that we ran at the beginning. Let's see if we have something else. No, so everything else is stuck, I guess. Yeah, everything is pending, but these 2 new calculations will be very fast. So it was only relevant to run the first one at the beginning. So now we can check what is going on, since it's still running. Now we can check, for example, the log files, and we will check the log relative to the first task, like the master task. And we see that we are almost at the last step. It is computing the final part, the correlation part of the self-energy. So most, like, let's say 1 minute, and more or less it's going to finish. We have already run all the others. And then let's maybe open this one directly. So you see here at the start, there is basically a summary of what we are doing. So it says CPU, but it's GPU. A summary of our parallel environment, what we are doing. So it's 4 tasks in all these types of calculations. And then you see this is the same as before. So we computed the dipoles, the kinematics elements. Then we have some input-output messages, memory messages, and then here it's starting to compute the response function at the various momenta. So 1, 2, 3, and so on. We have 19. So we keep going. Okay. After this, now it starts to go to the self-energy segment of the calculation. First, the exchange part, which is this one, was basically 1 second, as you can see. And finally, the correlation part, which is where we are now. Now, in order to proceed, we need to wait that these are completed. So, as you can see, already the MPI 16, where we were using 4 nodes, is basically already finished. And we can check this with this command. This time, we are checking the report file. So before, we opened the log files. And now we are opening the report files, which start by R, for the timing. And it seems that everything is now finished. Wait, what is this? 51 minutes. Sorry, this is one, sorry, I made a mistake. This is when you run with just 1 GPU. So it's basically serial calculation on the GPU card. For this system, you see, it takes a long time. If you run with 2, 20 minutes. The run that we did so far with 4 is basically 10 minutes. And I was expecting that at least the faster had finished, but it's not true. So they are both still running. So maybe we can wait 1 minute to let them finish. In the meantime, if you want to discuss something, well, you know what we could discuss actually? The script that we are going to use to plot the timings. If, yeah. Anyway, yeah. So we are, as before, we are going to use a Python script. So we just load the Python module here. You see that we have all these directories that are conveniently named in an organized way. So the script will just parse the number, the report files included in the various directories, and will sort them by MPI task number, right? So when you open a Python script, typically you go to the bottom to check the main part of the code. So here you see we are using some functions to open the report files in the various directories, get the number of tasks and the various timings related to the various sections. We get also the total time, and then we have a final function, which is this one, to just make the plot. So if we run it in this way, it will just print the help. And it will tell us, okay, you have to basically use the string at the beginning of your directories in order for me to be able to enter them. Let's check if we can actually do this. Okay, we are almost done. The one with the 8 MPI task is still going. So let's check here. Okay, we are almost at the end also here, finishing the correlation part of the self-energy, and then we will be able to plot it. Okay, so we're done. Now, if we grep the reports, we should get all the times, 1, 2, 4, 8, and 16. So we are fine. We run our Python script. And we have produced this PNG GW scaling figure. I'm not going to copy it on local, but we can look at it here. So this gives basically the total timings of our various calculations as a function of the number of MPI tasks, which in a GPU calculation means number of GPU cards used, one task per GPU card. We can say something, we can make some various considerations about this part. First of all, of course, we see that we are gaining a lot at the beginning, and at the end, at 16 tasks, we are almost reaching a plateau. For this particular small calculation, this means that allocating more resources to this will be a total waste of resources, because we are not going to get a reasonable speed up after this point of 16 tasks, right? So in principle, when we see this, we say, okay, we use either 8 or 16 if we really want to spend resources, but not more than this. Obviously, we did not optimize the parallelization structure of our calculation. We just put everything on empty bands. For example, if you remember, maybe there are ways to make it even faster, which I will discuss later. And also keep in mind that the reason why it plateaus so fast, let's say with just 4 nodes, we have already reached the top speed up, it's because we are still running a fairly small calculation. If we were to run a really large calculation with many atoms, with many electrons, with very large values for the conversion parameters, then Yambo will scale much better. And so Davide, in the first lecture of today, already showed you some plots about how well Yambo can scale also with thousands of MPI tasks, if you have a system, of course, large enough that can be meaningfully parallelized. Okay. Indeed, what I wanted to show you now is just, we don't have to run anything, but it's just a comparison. What if we did the same calculation, but on CPU instead of GPU, right? So you can also compile Yambo to be run on CPU. Of course, it's not the best way to do it on a machine like Leonardo, but you can do it. In this case, also the OpenMP threading becomes very relevant for the performance of your CPU-based calculations. And we run a version of a similar system, MOS2, with parameters a little bit changed, in order to compare GPU and CPU performance. This is still a small system, and we found that in the case of a CPU calculation, so in a Leonardo node, we have 32 CPUs. So a Leonardo node is made of 32 CPUs and 4 GPUs, right? So if we run on GPUs, it's pretty much straightforward. 1 MPI task per GPU, 4 MPI tasks per node. If we run on CPUs, we can manage the number of MPI tasks and OpenMP threads. And for the CPU calculation, we used here 16 MPI tasks and 2 OpenMP threads. So the product is 32, which is the number of our available processors. This ratio between MPI tasks and OpenMP threads depends a little bit on your system. The larger the system, the more stable the ratio. And we find that in general, with a regular system on this machine, you should use actually 4 MPI tasks only and 8 OpenMP threads. So this would be the default in general. Just for these small calculations, if you use instead this setup, is a bit faster. And so for these calculations, then we use still 4 nodes, for example, the largest one. But now we place 16 tasks because we have enough CPUs. And then we use 2 OpenMP threads. You see that in the Yambo input, let me open it again from here. We not only have parallel variables for the MPI tasks, but we also have parallel variable for OpenMP threading. Typically, they are set to 0. 0 does not mean don't use OpenMP threading. It means just use whatever number of threads is stored in this variable as environment variable OpenMP number of threads. So if we put 0 here, in this calculation, 2 threads will be used. Otherwise, you can just manually select also different number of threads from different sections of the code and so on. And this is the results. So it's still our tutorial system, so it's nothing super fancy. But you see that even at this level, the GPU calculation, which is in TIL, already achieves 2 times speed up with respect to the CPU calculation. So the speed up is the red curve, right? The blue is the CPU calculation, and the teal, the light blue, is the GPU calculation. So this we are comparing for each node. I remind you, we have 4 GPUs, so 4 tasks. So in the GPU case, we are running from 1 to 16 MPI tasks, while for the CPU calculation, we have 16 tasks per node. So already here we have a good speed up. Of course, the speed up increases more and more the larger our system. So we have already seen this figure in David's lecture, so I'm not going to discuss them again. These calculations, these tests were done on a different machine, but in any way similar to Leonardo. You see that when you go to massive calculations, massive systems, not only you have a very good speed up, very good scaling with respect of tasks, but also you have an enormous advantage if you run on a GPU, an accelerated system in GPUs. Okay, so now last part. This is still a discussion. We are not going to run anything about parallel calculations in Yambo. So what I was mentioning before, for our calculations, our scaling tests, we just parallelized over one channel, like for example, for the chi, the response function only on empty states. But of course, you can decide to split your tasks between different channels and check when you get the best performance. Typically in Yambo, it's best to prioritize parallelization over K points and empty states. So if you are starting a new system, you need to check a little bit how to make it more efficient. I would prioritize these two channels first, unless your system is very strange. And typically, both these channels give a very large speed up in the calculation. K maybe gives a faster calculation overall, but increases the memory load on the various tasks. While instead, if you parallelize over empty states, you have less memory per task. So if you are running a very large system and your GPU card only has, 16 gigabytes that you can load, and you are getting out of memory errors, increasing the parallelization over empty states will help you with that. Instead, if you don't have memory problems, maybe you can try to parallelize a bit also over K and see if it runs overall faster, the calculation. This depends on the system, on the machine, and on the type of calculation that you are doing. So if you're doing a GW calculation or a BSC calculation, let's say the most efficient configuration may be different. So it's all about testing and getting an idea of how it works and what is best to use, obviously. Okay, so I think this is all that we wanted to say about parallel execution, but in any case, maybe we can do a small break if you have some questions, or if anybody else from the tutors want to add some information, stuff like that. I cannot read the Zoom chat, so in that case, I ask the other tutors if they can please read it.
So let me add a comment, Andrea Ferretti here. So I think Fulvio has already described very well the situation of Yambo running on GPUs, but in order to give some figures, as from the numbers reported in the graphs Fulvio has been showing, typically the speed up you expect to have when running Yambo on GPUs with a sizable, decently sizable calculation as compared to CPU is about a factor 10 in the time to solution. Of course, this depends on which CPUs are mounted on the node, which CPUs are mounted on the node, the interconnects and so on. It's just a rule of thumb. But HPC machines, those that we have access to, are typically somehow balanced. So there's a ratio between the power, the computational power you get out of GPUs and that you can get out of CPUs. So you expect a number of this order. Also, the reason why to have more, that was also clearly explained, but it's probably worth to reiterate. The reasons to have more MPI tasks connecting to the same GPU is just because in the example here we were running very small systems. That is called oversubscription, and typically you don't want to have when running production kind of calculations. In that case, you want to have one MPI, one GPU. And also, since we are talking, I was also replying to the question about this aspect on the HackMD chat. The main point is that the first of all, we are talking about cores, not CPUs, in the sense that on Leonardo we have one CPU with 32 physical cores, and we want that CPU to handle the operating system, perform the I/O, does a number of tasks, should support MPI, and MPI should connect to the GPUs. So it's not really conceivable to have 32 GPUs on one node. Typically, there's a balance between the power of the GPUs and the power you have on the CPUs, keeping in mind that the CPU also has to do stuff. So the GPUs themselves do not carry or run an operating system. The operating system is run by the CPU. So the CPU has a lot of extra tasks, such that it requires, you cannot really fill it with a lot of MPI task targeting GPUs. And typically there's a ratio, a golden ratio that we see around in the existing HPC machines about the number of GPUs per node. Typically those range from 4 to 6 to 8. Those are typical numbers we see around, with the number of cores on the host instead ranging from 32, 64, or these numbers. Okay.
Yeah, very, very interesting technical details. So for us, it's something somewhat new, no? To make this transition and to think, okay, now we have to run GPUs and to code in a way that like it's amenable to GPUs. But it seems that the change is really happening. So we're happy that Yambo has made the change. Okay.
Yeah, I think that Fulvio, this is also a very important point to stress, is that it's not that we love GPUs and so we really want to go on GPUs, is that is a boundary condition that is happening now. That is happening at the level of the biggest machines we have around, but definitely GPUs are there and are everywhere. And I mean, within this trend, we'll have GPUs more and more. So I think that even if it's difficult somehow to get into, I mean, we have to learn something to move from CPUs to GPUs. I think it is really worth to do, because that is going to be the next future of HPC at least.
Okay, so I think now we can finish the tutorial with the last section, and finally we get some plot, some band structure results, right? So as before, I would suggest let's change into the last directory, 04 GW bands. Immediately submit this one. It should take 3 minutes, so it's not so much, but since maybe it can stuck into pending state, let's just submit this gpu_job.sh, and in the meantime we discuss what we are running. Here we have yet another save directory with an even larger system. The point here is that we want to have a band structure that is realistic. It's not converse, but at least looks like the real thing, right? And you've seen that here we switched from 12 times 12 times 1 to 18 times 18 times 1 in the K-point grid from the DFT quantum espresso calculation. We have also increased the vacuum separation between repeated copies of the simulation supercell. Before using 20 bores, now it's 30 bores. And so now we have more points. And if we check our new input, let's just go to the QPK range. You can see also here on the right. Now we are correcting 30 bands over 37 K points, which is the number of K points that you have in the irreducible brilliant zone if you are using a regularly spaced 18 times 18 grid. Also, you see which bands we are correcting. 25 and 26, if you recall, are valence bands, and 27 and 28 are conduction bands. So we are correcting 2 valence and 2 conduction bands. For all over the Brillouin zone, you can ask, okay, but if you just want to plot a band structure, you can just specify the indices of the points lying on the symmetry directions. And this is certainly true, and this is certainly what you could do, right? But imagine that after this GW calculation, we are not done. We want to also do a Bethe-Salpeter calculation on top of GW. Then you need the GW corrections over the whole Brillouin zone to feed into the Bethe-Salpeter equation. So typically, our workflow GW plus BSE requires you to correct the whole Brillouin zone over a reasonable amount of bands that you know will be important for the excitonic transitions. So this is what we are doing here, no? So, and this increases, of course, a lot the computational cost. It should be considered. So, if you want to not just plot a band structure, then you have to be prepared for a typically long simulation, but not so long now that we are running on GPUs, right? So now here, if it, okay, still going. Wait some time, but okay, we can still wait a little bit for it to finish. Let's maybe check. Let's maybe check the logs here. Okay, so you see here it's computing the screening. It is so it has to compute 37 transferred momentum points, right? But as you can see, it's going reasonably fast. So we just have to wait a little bit, and yeah, let's just wait. I see there is a Vanier 90 interpolation question on the ACMD file. Yes, the answer is that it is possible. Yambo is interfaced with Vanier 90 precisely to do this kind of interpolations. So in principle, it will allow you to, the response function, the chi, this one, you still have to converge. So this has to be computed on a fine mesh. But if you just want to then use Vanier interpolation, this QPK range instead could be like a sub-mesh, even very coarse, right? And then you will interface these results with Vanier 90, and you will obtain an interpolated grid of quasi-particle correction, which in principle is like infinitely dense. Which is quite cool. So there are guides about how to use Yambo with Vanier 90. Maybe some people can paste some links. Keep in mind that if you know how Vanier 90 works, typically you pay a price for using few K points, and that is that you have to correct more bands because you have to find the interpolation windows so that interpolation is okay. So it is a balance, but typically, if you want to plot band structure, it should be much faster using Vanier 90. Instead, if you want to do a GW plus BSE calculation, it really depends because GW and BSE can converge with different densities of K points. So in the assumption that the GW converge, the assumption that you have the GW calculation on a coarse mesh and you need to do a BSE on a very fine mesh, then you can compute GW, interpolate on the BSE mesh, and then do the BSE calculation. This is convenient or not, this depends a little bit on the system, but it could be very convenient in some cases. Okay, so now we should be finished here. So these sbatch commands, basically they don't work at all. But here we are finished. So what do we do now? Now we want to plot a band structure. So we will indeed interpolate these results right now, but it's not the Vanier physics-based interpolation. It will just be a Fourier interpolation just to show a reasonable band structure, okay? And we will do it with YPP, which is a Yambo executable for pre- and post-processing capabilities. So in principle, we also have a Python-based layer interface for Yambo. It's called Yambo Pi. It was mentioned before also in the replies. Yambo Pi allows you to really go in and read and work with the binary files of the NetCDF databases instead of just working with the human readable files. And you can get various quantities that typically are not printed by Yambo. But for us, for the tutorial, we don't really need that. We can just do a simple calculation with YPP. So first of all, we enter into a computing node. And then we just load the Yambo again inside the node. Now you will see we have access also to the YPP executable. As for the Yambo executable, we can create an input, we can run the help of YPP, and here again, as before, we can check it, and depending on what we want to do. In particular, we are interested in this electron flag, which is abbreviated -S. And if we check the help, you see that it has these sub flags, depending on what you want to compute. And we are interested in a flag called DOS, even though we are just going to plot the band structure. So YPP -electron or -S. Sorry, we are interested in bands. Don't know why I said DOS. We are interested in B because we want to do a band structure. So -electron B. And then we already specify the name of our input file, YPP bands. Okay, if we open it. Here is the text, again, a large number of variables, but in the end, we want to modify really a small number, right? First of all, we go here, the interpolation mode. The default is nearest neighbor, but this really sucks. So we want to put the bootstrap approach, which is basically Fourier interpolation. Then here we place the lattice parameter for MOS2. So this, I mean, now I'm copying it from the tutorial page, but you can get it from the report files. You remember when you initialize the save directory, then this information is also printed there for sure. Now, which bands we have? Well, we have the bands from 25 to 28. So we are going to correct those. Then how many steps we want in our band structure, so interpolated steps, 100. And then which circuit or path in the Brillouin zone we need to correct, just copying it. So this will be the gamma point, 0, 0, 0, the M point, 0, 1/2, 0, the K point, 1/3, 1/3, 0, and then we go back, we close the circuit to the gamma point. Okay, so we are telling YPP, listen, take the energy values, interpolate them in steps of 100 for these bands, 25, 28, along this circuit. And so now this is what we are going to do. To be quite fast. Okay. So you see that we have produced some outputs, these O.dot files. We don't really care for this tutorial, at least, about most of them, so we will remove them. Just one thing, though. We have these O.bands interpolated, we can open it. This is difficult to read, but we have, you see the k-axis, and then we have the energy values at each k, this k modulus for the 25, 26, 27, and so on bands. These, however, are not the GW bands that we just calculated, because we didn't specify it to YPP. So YPP just took the DFT Concham bands and interpolated those bands. So we need also those for the comparison, so we are happy that we did that, but we just changed the name of this output so that it's clear what it is. And then we just make all the rest of the other outputs that we don't want to use, we make it disappear into a directory. Okay, so now we have this output, O.DFT band. Good. Now we have to finally interpolate also the GW bands, right? So we open again our input, and we add a very important string, this one. This one is going to tell YPP to go inside this directory GW bands, take this database ndb.qp. This is the database containing the quasi-particle corrections, and use it as energies. This is the same string that you will use if you want to include a GW calculation in a Bethe-Salpeter run. So it's very important, you have to tell the code where to find the quasi-particle calculation. Otherwise, Yambo will use DFT values, okay? Perfect. And now we can, again, run the interpolation step. We're almost finished. We will be on time as well. It's 5 minutes. Okay, so now again we have a new interpolated file. Now we change it and we call it GW. Okay. And then again, we just for cleanup, let's say that we remove the other outputs that we don't we won't use. Okay, so now we have these two files. We can plot it, of course. So first of all, we load the Python module, and you see this. Basically, this function is a Python function. Is going to read these two output files and plot it in a kind of fancy way. So with all the labels, colors, and so on. If we just run it, it's a good idea when you do a Python script to, if you run it without options, to just print the help. I guess it's a good idea when you do any script. And in this case, we just have to give it like you see here, we need to give it the outputs, so DFT bands, GW bands, and then the number of bands in this case. So we have 4 bands, and therefore we give this number, we go, and as you can see here, we have produced a GW_band.png figure. I exit the computing node. You can SCP this file and visualize it, and you should get exactly this visualization. So in red, we have the interpolated DFT bands on the circuit that we chose, typical circuit for an hexagonal system, and in blue, the GW correction. Now, it's time to analyze a little bit our results. We can compare, fortunately, somebody did a calculation, a converse calculation on monolayer MOS2. This also was done with Yambo. And we can kind of compare a little bit what we found with what is there. So the GW bands here are the continuous lines in the published figure. You see that we more or less have a very good description, even if our system is not extremely well conversed. There are some differences, though. One is typically due to convergence, and I'm going to just say it. It's just that the band gap is a little bit different, right? So here we have a band gap of below 3 electron volts, and here instead we are above 3 electron volts, right? So means that we did not use the W average method for this calculation, for example. Odds are, if we used it, we would have a much better bandgap right now. And then there is a second feature that is a bit more subtle, and you can already see it in this plot. I don't know if you notice, but the DFT bandgap is a direct bandgap, and the GW bandgap becomes indirect. Because the correction is not simply a rigid shift, you have a stretching of the bands, and so clearly some the bands in this gamma K region are shifted less than at K. This is actually a very subtle effect. There are actually papers dedicated to kind of explain if the gap should be indirect or not at the GW level, and entirely depends on the mostly depends on the starting point of our simulations. Since we are doing G naught, W naught, so it's a one-shot non-self-consistent GW, there is a definite dependence on the starting point, and in particular, the relative position of these two valleys in a GW. In DFT, they are always like this, but in a GW calculation, they will depend on the geometry of the system. So, for example, the lattice parameter that you use, how do you optimize it, which pseudo potentials, and so on, and also, of course, on the type pseudo potential that you are using. So as you can see, these are all, this is much more subtle than just converging the bandgap, but can have important effects if the calculation is not correct, because you can mistake indirect bandgap for a direct bandgap. And this kind of overall tells you like there is an inherent difficulty in running this type of many-body calculations, that you have to be very careful, you have to know what you are doing in a sense. It's not enough to just prepare an input and press enter or just do a trivial convergence study. You also have to know your system and so on. You see that here in the correct calculation, the bandgap is still direct. So with this, I think we can close the tutorial. As you see from the last paragraph, you can, for news and for info about Yambo, there is the website. Instead, for tutorials and technical information, you can go to the Yambo wiki. So we have many tutorials there. Some are related to past schools and some generic tutorials. And finally, if you start using Yambo and you find that you have issues, either in running it or in compiling it, for example, you can write about those issues on the Yambo forum, and typically some people who know what to do will reply to you. Okay, I think let's just finally check if we have some. Okay, everything here is replied to. So for me, I guess that's all. Thank you for your attention, and I give the floor to whoever else will close it.